What if I told you that a single Japanese engineer solved a problem that had Detroit's best minds stumped for over a decade? A problem so fundamental that GM and Ford collectively spent millions of dollars and thousands of engineering hours trying to crack it, only to walk away defeated. This is the story of how Kenichi Yamamoto outsmarted the entire American automotive industry with a material so unconventional, so brilliantly simple, that when Detroit engineers finally learned his secret, they couldn't believe they'd missed it. Picture this. It's 1960, and inside General Motors Technical Center in Warren, Michigan, a team of engineers watches in horror as another rotary engine tears itself apart on the test stand. The apex seals, those critical triangular tips that form the combustion chamber in a rotary engine, have failed again. Metal shavings scatter through the housing like shrapnel. The engine managed just 8,000 miles before catastrophic failure. Down the road at Ford's Dearborn Labs, the story is identical. Their rotary prototypes are eating themselves alive, destroying apex seals faster than they can design new ones. Chrysler's engineers fare no better. After burning through $50 million in development costs, that's $500 million in today's money, Detroit's Big Three are ready to declare the rotary engine an engineering impossibility. Meanwhile, 6,000 miles away in Hiroshima, a 39-year-old engineer named Kenichi Yamamoto is staring at the same problem with completely different eyes. While Detroit was throwing harder and harder metals at the problem, Yamamoto was about to do something that would change automotive engineering forever. He was going to stop thinking like a metallurgist and start thinking like a chemist. The rotary engine should have been Detroit's triumph. After all, when Felix Wankel unveiled his revolutionary engine design in 1957, it promised everything American automakers craved. No reciprocating pistons meant incredible smoothness. Fewer moving parts meant simplified production. The compact size meant more room for styling. And the power potential? Through the roof. NSU's early calculations suggested that a rotary engine the size of a watermelon could produce the same power as a V8 twice its weight. It was the holy grail of automotive propulsion, or so everyone thought. By 1959, the licensing frenzy had begun. General Motors paid NSU $2.5 million for rotary development rights. Ford followed with their own multi-million-dollar deal. Curtiss Wright secured the American aircraft rights. Even Mercedes-Benz bought in. The race was on to bring the rotary engine to mass production, and with Detroit's engineering might and deep pockets, everyone assumed the Americans would cross the finish line first. But here's where it gets interesting. The rotary engine's Achilles heel wasn't its radical design or its unconventional combustion cycle. It was a component smaller than your thumb, the apex seal. These tiny triangular seals had to perform an impossible job. As the rotor spun inside its epitrochoidal housing at up to 9,000 RPM, the apex seals had to maintain perfect contact with the housing wall while enduring temperatures exceeding 100 degrees Fahrenheit, pressure differentials of 1,000 psi, and sliding velocities that would destroy conventional piston rings in minutes. Detroit attacked the problem with brute force. GM's engineers tried cast iron seals with chrome plating, failed at 5,000 miles. Ford experimented with tool steel alloys hardened to 60 Rockwell C, made it to 7,500 miles before chattering themselves to death. Chrysler went exotic, testing tungsten carbide and even ceramic compositions. The ceramics shattered. The carbides wore grooves in the housing that looked like someone had taken a grinding wheel to them. By 1963, internal memos at GM described the apex seal problem as insurmountable with current materials technology. Enter Toyo Kogyo, the company that would become Mazda. Unlike the American giants, this relatively small Japanese manufacturer couldn't afford to fail. They'd licensed the rotary technology from NSU in 1961, betting the company's entire future on making it work. President Tsuneji Matsuda had declared that Toyo Kogyo would either succeed with the Rotary or cease to exist as an independent company. No pressure, right? Matsuda assembled a team of 47 engineers, they called themselves the Rotary 47, and put Kenichi Yamamoto in charge of solving the apex seal crisis. Yamamoto wasn't your typical automotive engineer. He'd studied mechanical engineering at Tokyo Imperial University, but had spent years working on industrial furnaces and high-temperature materials. This background would prove crucial. While Detroit's engineers kept searching for the perfect metal, Yamamoto asked a different question. Why does it have to be metal at all? His team began experimenting with carbon-aluminum composites, materials more commonly found in industrial applications than automotive engines. Carbon offered self-lubricating properties. Aluminum provided thermal conductivity. But the real genius was in how Yamamoto combined them. The breakthrough came in late 1962. Yamamoto's team developed a proprietary process that embedded aluminum particles within a carbon matrix, then reinforced the structure with hair-thin steel fibers. The exact composition remained a closely guarded secret for decades, but we now know the formula: 70% high-density carbon, 25% aluminum powder, 5% steel fiber reinforcement. The material was pressed at 2,000 tons per square inch and centered at Walhorst 800 degrees Fahrenheit in an inert atmosphere. The result was an apex seal that seemed to violate everything Detroit knew about engine materials. Let me put that in perspective. GM's best metal seals were failing because they couldn't handle the combination of heat, friction, and pressure. They'd either wear too quickly, score the housing, or lose their spring tension and leak compression. Yamamoto's carbon aluminum seals did something revolutionary. They got better with use. The carbon would gradually polish the chrome housing surface while depositing a microscopic lubricating layer. The aluminum conducted heat away from the seal face. The steel fibers maintained dimensional stability. It was materials science poetry. Testing began in early 1963. The first prototype ran for 100 hours straight, already exceeding anything Detroit had achieved. Then 200 hours, then 300. When they finally tore down the engine after 400 hours of continuous operation, the apex seals showed minimal wear. More importantly, the housing surface looked better than when they'd started. The seals had actually improved the surface finish. But Yamamoto wasn't satisfied. The team discovered that by adding a tiny amount of antimony, less than 0.5%, they could increase the seal's high-temperature stability by 40%. They refined the manufacturing process, developing a multi-stage sintering technique that created a gradient structure, harder at the surface, more flexible at the core. By mid-1963, their apex seals were surviving 1,000-hour durability tests. That's equivalent to 60,000 miles of driving. Meanwhile, at GM's technical center, engineers were still convinced that metal was the answer. An internal report from December 1963 stated, "The Japanese approach using carbon-based materials represents a fundamental misunderstanding of combustion engine requirements. High-temperature metal alloys remain the only viable solution." Ford's engineers were equally dismissive. A leaked memo from 1964 referred to Mazda's carbon seal approach as technically naive and commercially impractical. Here's the kicker. While Detroit was dismissing Yamamoto's solution, he was already solving the next problem. The carbon aluminum seals worked beautifully, but they needed a specific surface treatment on the rotor housing to achieve optimal performance. Yamamoto developed a proprietary chrome plating process that created a surface with microscopic oil retention pockets, invisible to the naked eye but crucial for seal longevity. The plating thickness was controlled to within 0.01 inches. The surface hardness reached 72 Rockwell C. The porosity was engineered to hold exactly 0.3 cubic centimeters of oil per square inch. By 1964, Mazda's rotary engines were achieving something Detroit said was impossible. The test engines were running 200,000 miles without apex seal replacement. The compression remained within 5% of new specifications. Oil consumption stayed under 1 quart per 1,000 miles. The power output actually increased slightly as the seals bedded in. These weren't laboratory queens either. Mazda was testing in the brutal heat of summer and the sub-zero winters of northern Japan. The Cosmo Sport's development began in earnest in 1965. This would be Mazda's moonshot, the world's first mass-production rotary car. The engine, designated 10A, displaced just 982 cc but produced 110 horsepower at 7,000 RPM. That's 112 horsepower per liter, a specific output that embarrassed contemporary American V8s, making 60 horsepower per liter. The engine weighed just 224 pounds, complete with all accessories. A comparable piston engine producing the same power would weigh nearly 400 pounds. But the real achievement was reliability. Mazda tortured the Cosmo prototypes in ways that would make Detroit's validation engineers wince. They ran them flat out for 48 hours straight at the Miyoshi Proving Grounds. They drove them up Mount Fuji in summer with the cooling fans disconnected. They subjected them to 40-degree cold starts in Hokkaido. The apex seals survived everything. Production began in May 1967. The Cosmo Sport wasn't just a technological showcase, it was a reliability statement. Mazda offered a 50,000-mile warranty on the apex seals at a time when most manufacturers wouldn't guarantee piston rings past 24,000 miles. The automotive press was stunned. Road and Track called it the most significant advancement in internal combustion technology since the turbocharger. Car and Driver declared the Rotary the future of automotive propulsion. Detroit's response? Panic, followed by furious reverse engineering. GM purchased 3 Cosmos through intermediaries in Japan. Ford bought 5. When they tore down the engines and discovered Yamamoto's carbon aluminum seals, the reaction was equal parts amazement and embarrassment. A GM engineer who worked on the teardown later recalled, "We'd been so focused on finding the ultimate metal that we never considered going outside the metallurgy box. It was like spending years trying to build a better hammer when what you needed was a screwdriver." The numbers tell the story. By 1968, GM had spent an estimated $100 million on rotary development with nothing to show for it. Ford had burned through $75 million, Chrysler had written off $50 million combined, Detroit had invested enough money to develop an entirely new car platform, and they had nothing but boxes of failed apex seals to show for it. Mazda, working with a development budget that was a fraction of any single American manufacturer, had cracked the code. But here's where Yamamoto's genius really shined. He didn't just solve the apex seal problem, he created an entire ecosystem of rotary technology. The oil injection system that precisely metered lubricant to the apex seals, the thermal reactor that cleaned up the rotary's inherently dirty exhaust, the peripheral port induction system that would later enable incredible power outputs. The 1968 R100 Coupe brought rotary power to the masses. Priced at $2,795, it undercut the Porsche 911 by $4,000 while offering similar performance. The 100-horsepower 10A engine propelled the 1,960-pound coupe to 60 mph in 10.9 seconds and onto a top speed of 109 mph. But it was the engine's character that captivated enthusiasts. The turbine-smooth power delivery, the 7,000 RPM, redline that it reached without a hint of vibration, the distinctive humming exhaust note that sounded like nothing else on the road. Let that sink in for a moment. A Japanese company with fewer engineers than GM had in its cafeteria staff had brought to market what America's industrial giants couldn't, and it wasn't a fluke. The R100 was followed by the RX-2, RX-3, and the legendary RX-4. Each iteration refined Yamamoto's apex seal technology further. By 1970, the seals were lasting 300,000 miles in taxi service in Japan. GM's response was perhaps the most telling. In 1970, they announced the development of a revolutionary rotary engine for the 1974 Vega. Ed Cole, GM's president, promised it would make every other engine obsolete. Behind the scenes, GM engineers were frantically trying to develop their own apex seal solution. They couldn't use Mazda's design. It was protected by 37 separate patents. So they tried to engineer around it. The GM Rotary used a three-piece apex seal with a cast iron base, a ceramic insert, and a tungsten carbide tip. In theory, it combined the best properties of each material. In practice, it was a nightmare. The different thermal expansion rates caused the pieces to separate at high temperatures. The complex assembly was nearly impossible to manufacture consistently. Worst of all, the seals cost $400 each to produce, 40 times more expensive than Yamamoto's carbon aluminum design. By September 1974, GM quietly canceled the Rotary Vega program. They'd spent another $300 million and had produced exactly 0 production engines. The official reason was the oil crisis and emissions concerns. The real reason, according to internal documents that surfaced years later, was that they still couldn't match the reliability of Mazda's 5-year-old apex seal design. Ford's Rotary program met a similar fate. After spending $400 million in total development costs, they shelved their Rotary project in 1975. The final insult? When Ford engineers benchmarked a 1974 Mazda RX-4, they found the apex seals still measured within factory specifications after 150,000 miles of testing. Ford's best experimental seals were failing at 20,000, but Yamamoto wasn't resting on his laurels. In 1973, he was promoted to managing director of Mazda and immediately pushed for more radical development. The 12A engine debuted with improved apex seals featuring a new aluminum silicon composite layer that reduced friction by another 15%. The 13B followed with 3-piece apex seals that incorporated ceramic particles for even better heat resistance. Each generation built on the foundation of that original carbon aluminum breakthrough. The RX-7, launched in 1978, became the ultimate vindication of Yamamoto's vision. Here was a sports car that could compete with Porsche and Corvette at half the price. The 12A engine, with its improved apex seals, was so reliable that Sports Car Club of America had to ban it from certain racing classes. It was dominating everything else. By 1980, Mazda had sold over 1 million Rotary-powered vehicles worldwide. The apex seals that Detroit said couldn't last 10,000 miles were now routinely surviving 200,000 miles in street use. The racing success was even more impressive. In the 1981 24 Hours of Daytona, a Mazda RX-7 finished first in the GTU class after running flat out for 24 straight hours. The post-race teardown revealed apex seals that looked barely used. At Le Mans, the rotary-powered Mazda 717C ran for 24 hours at speeds exceeding 200 mph. The apex seals survived temperatures that would have melted Detroit's metal seals into puddles. Think about that for a second. The same seals that GM's engineers declared impossible were now winning the world's most grueling endurance races. The carbon aluminum composite that Ford dismissed as naive was outlasting everything else on the track. Yamamoto's misunderstanding of combustion engine requirements was rewriting the requirements entirely. The technical evolution continued through the 1980s. The 13B RU engine in the third-generation RX-7 featured 2-piece apex seals with a carbon base and a special iron-chromium molybdenum alloy tip. The combination delivered 205 horsepower from just 1.3 liters while maintaining exceptional reliability. The apex seals could handle boost pressures up to 15 psi and exhaust temperatures exceeding 1,800 degrees Fahrenheit. But the ultimate triumph came at Le Mans in 1991. The Mazda 787B, powered by a four-rotor R26B engine using Yamamoto's evolved Apex Seal technology, didn't just compete, it won overall. This wasn't just beating other rotary engines, this was defeating Porsche, Mercedes, Jaguar, and every other manufacturer on the planet. The R26B screamed to 10,500 RPM and produced 700 horsepower from just 2.6 liters. During the 24-hour race, the engine never missed a beat. Post-race inspection showed the Apex seals had wear measurements in the thousandths of an inch. The victory was so dominant that rotary engines were banned from Le Mans the following year. Let me repeat that. Yamamoto's Apex Seal technology was so successful that racing organizers had to outlaw it to give everyone else a chance. Meanwhile, Detroit's relationship with the Rotary had become a cautionary tale in business schools. GM's total investment in failed Rotary development exceeded $500 million. Ford lost $400 million. American Motors Corporation spent $60 million on a Rotary program that never produced a single engine. Combined, American manufacturers had burned through nearly $1 billion trying to solve a problem that Yamamoto cracked with a $10 million budget. The irony wasn't lost on industry observers. In 1985, Automotive News published an analysis showing that if GM had simply licensed Mazda's Apex Seal technology in 1968, they could have had rotary engines in production by 1970 at a total cost of less than $50 million. Instead, their pride and conviction that American engineering superiority would prevail cost them 20 times that amount and delivered nothing. But here's what makes Yamamoto's story even more remarkable. He could have gouged the industry. Mazda could have locked down their Apex Seal technology and forced everyone to pay astronomical licensing fees. Instead, Yamamoto published detailed technical papers about the principles behind carbon aluminum seals. He spoke at engineering conferences, sharing the fundamental insights that made the breakthrough possible. He believed that advancing automotive technology was more important than protecting every trade secret. Not that Mazda gave everything away. The exact manufacturing processes, the specific material ratios, the surface treatment techniques, these remained closely guarded secrets. But Yamamoto shared enough that other engineers could learn from his approach. He revolutionized how the industry thought about material selection. Instead of always defaulting to metals, engineers began exploring composites, ceramics, and hybrid materials. The ripple effects extended far beyond rotary engines. Modern Formula One brake discs use carbon composites that trace their lineage back to Yamamoto's Apex Seal research. The silicon aluminum pistons in high-performance engines borrowed insights from his thermal management solutions. Even Tesla's electric motor bearings use composite materials that evolved from rotary seal technology. Yamamoto didn't just solve one problem. He opened an entire field of materials science to automotive applications. The RX-8, launched in 2003, represented the culmination of 40 years of Apex Seal evolution. The Renesas engine featured side exhaust ports that reduced thermal stress on the seals. The latest generation seals used a three-layer design, a carbon fiber reinforced base, an aluminum ceramic intermediate layer, and a chrome molybdenum steel contact surface. They were rated for 150,000 miles of normal use, 15 times longer than Detroit's best experimental seals from the 1960s. But the real measure of Yamamoto's genius isn't just in the numbers, it's in how he approached the problem. While Detroit threw money and conventional thinking at the challenge, Yamamoto questioned fundamental assumptions. While American engineers insisted on metal because that's what they'd always used, Yamamoto asked why. While the big three competed against each other in secrecy, Yamamoto built on knowledge from multiple industries. The financial impact was staggering. Mazda generated over $50 billion in revenue from rotary-powered vehicles between 1967 and 2012. The RX-7 alone sold 8,634 units globally. The technology created an entire ecosystem of suppliers, tuners, and racing teams. Estimates suggest the rotary engine industry, parts, service, racing, aftermarket, generated over $100 billion in economic activity worldwide. Compare that to Detroit's losses. Not just the $1 billion in failed development, but the opportunity cost. The market share lost to Mazda and other Japanese manufacturers who were willing to think differently. The engineering talent that spent years working on dead-end solutions. The reputation damage from very publicly failing at something a small Japanese company accomplished with ease. In 2012, when Mazda ended RX-8 production, it marked the temporary end of rotary production cars. But the Apex Seal technology lives on. Mazda continues developing rotary engines as range extenders for electric vehicles. The seals in these new engines are direct descendants of Yamamoto's 1962 breakthrough, now incorporating graphene enhancement and nanostructured surfaces that would have seemed like science fiction in the 1960s. Other manufacturers have finally caught up, sort of. Audi's 2013 A1 e-tron concept used a rotary range extender with Apex seals licensed from Mazda. Liquid Piston's revolutionary X engine uses Apex seals based on Yamamoto's carbon composite principles. Even aerospace companies developing rotary engines for drones and small aircraft start with his fundamental insights. Kenichi Yamamoto passed away in 2017 at age 95, having spent his entire career at Mazda. His obituary in the New York Times called him the engineer who proved Detroit wrong. But that understates his achievement. He didn't just prove them wrong, he showed them a completely different way of thinking about engineering problems. The lesson here isn't just about Apex seals or rotary engines. It's about the danger of assuming that the way things have always been done is the way they must be done. It's about the power of questioning fundamental assumptions. It's about how a single engineer with a different perspective can outsmart an entire industry's conventional wisdom. When modern engineers face seemingly impossible challenges, whether it's battery technology for electric vehicles, hydrogen storage for fuel cells, or heat management for hypersonic aircraft, they often invoke Yamamoto's example. Don't just try harder with the same approach. Step back. Question everything. Look outside your field. The solution might not be a better version of what exists. It might be something entirely different. Today, when you see a Mazda RX Vision concept car or hear about their SkyActiv R rotary development, remember that it all traces back to one engineer who refused to accept that metal was the only answer. One engineer who looked at carbon and aluminum, materials nobody associated with engine internals, and saw a solution everyone else missed. One engineer who understood that sometimes the secret to solving an impossible problem isn't working harder. It's thinking differently. The American automotive industry learned a painful lesson from Kenichi Yamamoto. Technological superiority isn't guaranteed by size, budget, or tradition. It's earned by those willing to challenge assumptions and explore the impossible. Yamamoto didn't just outsmart Detroit with a clever trick. He revolutionized how we think about materials, about problem solving, about what's possible when you refuse to accept that something can't be done. His carbon aluminum Apex seals weren't just a technical solution. They were a philosophy made manifest. A reminder that the next breakthrough might not come from doing the same thing better, but from doing something completely different. A proof that one engineer with the right idea can indeed change everything. What do you think would have happened if Detroit had been willing to think outside the metal box in 1960? Could GM or Ford have beaten Mazda to the rotary breakthrough if they'd approached it differently? Drop your thoughts in the comments below, and don't forget to subscribe for more stories of engineering brilliance that changed the automotive world. Until next time, keep questioning what's possible.